Hello everybody, welcome back for the second half of the video now. Previously we've finished up the epithelial tissue, and now we're going to go ahead and move on to the next segment, which is the connective tissue. And then after that we'll do a little bit of review for all the slides that we have. Alright, so let's go ahead and skip past all of these guys. Finally, the connective tissue. We've previously described the epithelial tissue as the functional aspect of an organ, right? This was essentially how the organ was remembered, like exactly what that organ did and what it was useful for. Well, now we're looking at the connective tissue. The connective tissue can also be described as the stroma, which pretty much directly translates from the Latin as meaning support. So all of the connective tissues that we're going to describe is more so for support of the body, maintaining posture, keeping the body, basically all the organs suspended in their respective cavities, and making sure that if there is any distortion that occurs in the body, we can actually revert back to our original shape. So we have three different types of situations here, or three different types of categories. We have the connective tissue proper, we have fluid connective tissue, and we have supporting connective tissue. So luckily here, we have some good definitions of what those three mean. Connective tissue proper is what we typically think about when we think of connective tissue and how they support the organs. Our fluid connective tissue is going to be pretty much just categorized to blood and lymph. So anything that has to do with that's flowing through our blood vessels, this is going to be our fluid connective tissue. And then finally, the supportive connective tissue is going to be stuff that is densely packed, that is going to allow for support more so of the entire body rather than the organs themselves. But here we can see the tissue proper. This is going to be a big topic that we're going to be talking about first. So taking a look here, we have a few different types here. We have our dense and our loose. So these are the two subcategories of our connective tissue proper. We have dense connective tissue proper, and we have loose connective tissue proper. And naturally, of course, these guys are also going to get their own subcategories of regular, irregular, elastic, and then loose areolar, adipose, and reticular. Now let's go ahead and focus on our dense type first. This is filled of collagenous tissue, which means these are very strong bonds that are going to go from point A to point B for the most part. They have like a very specific outline to them. So let's take a look at our collagen fibers for dense regular, dense irregular, and elastic. So first up, we have our dense regular connective tissue. Now whenever I think of something that's regular, I always think of something that's very ordered. Something that's very follows the rules, follows the regulations. That's what I kind of see whenever I see this guy, right? Everything's running in a parallel line, everything's kind of smooth and working well together, and there's a lot of order of like what we're trying to accomplish here. So here you can see a basic definition is that collagen fibers dominate and they're arranged in parallel to each other and are tightly packed. Now, excuse me, sorry about that. One of the most important areas that we need these dense regular fibers is going to be found inside of our tendons, inside of our ligaments. And the reason for this is because we want to think about, okay, well, what kind of function are we dealing with dense regular? For dense regular, there's a few pros and cons in terms of its parallel organization. For our pro, all these collagen fibers all coming from the same spot and all going to the same location, this makes it very, very strong material, very, very dense and strong material that can pretty much contract and pull on any ligament or muscle kind of looking at. Like this muscle, for example, this triceps. These tendons are really, really strong in their one direction that they're facing. But the downside is that they are only strong in that one direction. If you try to utilize these collagen fibers in any other direction, they simply would not work because that would be running perpendicular. That force would be running perpendicular to these lines. So whatever force is parallel with these lines, that's good. It's super strong in that direction, but any other direction, it's not going to be that good. Taking a look at our dense irregular connective tissue. So compared to our dense regular connective tissue, the dense irregular is more of like the crackhead cousin. It's very chaotic. There's no sense of pattern or direction. It's just kind of all over the place. Now, this also has its own pros and cons. Now, the first pro is that, or I guess we'll discuss it at the same time. Previously, we said that our dense regular can only go in one direction, and it was still super strong. Our dense irregular, so even though it's not nearly as strong as the dense regular, because dense regular is packed in tight into one area, our dense irregular is fairly strong in multiple directions, so it can resist distortion in multiple directions. So take your skin for example. Your skin is one of the easiest locations to think about when you're coming to dense irregular connective tissue. No matter which way I pull on my skin, no matter which way I pinch it or distort it, it is able to withstand that distortion. So this is kind of the benefit of having no consistent arrangement, is that it can go in many directions. It can resist stress in many directions. Here's the final type of our dense regular connect or sorry. There's the final type of our dense connective tissue. Is the elastic connective tissue. So the elastic connective tissue, once again, it's considered dense because it has the multiple layers of collagenous fibers all kind of working on top of one another. But this is going to actually be the form of elastic because we can actually see some spacing that occurs between the collagenous fibers. So this is going to allow for sizable expansion, permits expansion and contraction of various organs and lungs and blood vessels. One of the biggest locations this is also going to be found in is inside of the vertebral column to basically cushion shock. So whenever you're dealing with jumping from a high ground and landing on your feet, you kind of feel that reverberation of force kind of traveling up. That elastic connective tissue is going to allow for that expansion to pretty much keep your vertebrae stabilized, your backbone stabilized. Now moving on to loose connective tissue. So we have three different types: areolar, adipose, and reticular. And one of the biggest functions that these three tissue types share together is the act of cushioning. So the areolar, adipose, and reticular connective tissue all share the act of cushioning. That is one of the major functions that is shared among them. Excuse me again. So, taking a look at our loose areolar connective tissue, once again we see that it cushions organs. It's going to provide support and independent movement. So this is especially important in various organs that we find around our respiratory tract and inside of our GI tract as well. Because we want to think about our lungs, right? Our lungs want to be able to expand with air. And here we can see that, there's also the same term, areolar, air. So whenever you're thinking of areolar, you're thinking of air, you should be thinking about your lungs. This allows for the expansion of your lungs, can distort without damage because of its very open framework. That's one of the easiest ways to identify it, is to notice all this air or open space between the fibers that are kind of existing throughout. Here, taking a look at adipose tissue. So, adipose tissue is literally your fat cells. This is exactly the same thing. You can use them alternatively. Adipose tissue are your fat cells. Once again, your adipose tissue or fat cells are going to provide cushioning, right? So that's like all loose connective tissue. They all provide cushioning. But your adipose tissue is actually going to add a few additional details. It's going to provide insulation, which is to reduce heat loss, and it's going to act as a storage of energy. So one of the biggest examples that I like to think about in terms of loose connective tissue with our adipose tissue is I like to think about hibernation. So animals that go into hibernation during winter, they actually like to build up a lot of this adipose tissue for two main reasons. It stores energy and it reduces the heat loss, because obviously you're in winter, it's going to get very cold. So we can use our adipose tissue to kind of retain all that heat. And then finally, looking onto loose connective tissue for the reticular type of connective tissue, the general idea of what the function is, it is just going to provide a supporting framework. So imagine you're drawing an outline of the liver. That drawing of the outline of the liver would be made out of these reticular fibers, and it's just to basically support any kind of liver or any kind of these exact organs kind of suspended in the cavities. Alright, so moving on to blood, bone, and cartilage. So, luckily for you guys, the only thing that I'm going to have you recognize for blood is just this slide right here. If you can recognize that this slide is indeed blood, then you are solid for the quiz and for the exam, at least with regards to my class. The reason why I don't go into too much detail about blood is because blood is a huge topic for Bio 202 as well as Bio 211, and we have to get into a lot more detail about it then. But for now, just identify that this histology slide is in fact blood. These small little donut holes that my laser pointer is going over, these are all our erythrocytes. Those are the red blood cells that carry oxygen. And then the purplish figures that we can kind of see over here, the ones that are stained, these guys are our leukocytes, which are the white blood cells that fight infections. And you might see these little small tiny segments over here every once in a while too that are much smaller than our erythrocytes. Those would be considered our platelets or thrombocytes, which help to clot blood. Alright, so taking a look at our supporting connective tissue. Now first up we have bone, right? So for our bone we have two different types. We have compact bone, and these are the two additional names for the compact bone. It's cortical or dense. And then we have spongy bone, which you can also call it cancellous or trabecular. Now taking a look at the general outlining of how most bones are formed, we can see this hard outer surface, right? That's going to be the compact bone. So the compact bone is essentially establishing the hard outer surface that's going to be very important in protection against the outside world. But on the inside, we see all of this kind of branching of bone that's kind of occurring on. And as you know, the other name for spongy bone is trabecular bone. Trabecular actually translates as meaning branching. So you can kind of see why they would call it trabecular bone, right? Because it's branching all over the place. And the biggest idea of why we want the spongy bone in the center of the bone mass is to allow for dispersion of force. So imagine we take an object. Let's see if I can get my pen. We take an object, and this is like 5 kilograms. Well, I tried my best at drawing a 5. There we go. This is 5 kilograms, and we're putting a lot of pressure onto the bone right here. Because of this branching inner network, the dispersion of force is actually going to travel throughout the bone, so it's less likely to break. And it's easier to deal with the stress that way. It's easier to deal with the stress that way if it's dispersed throughout the bone. Alright, so taking a look at our simple unit here, this is all occurring inside of our compact bone. Now, as we can see, we have what is known as an osteon. Now, an osteon is essentially one functional unit of the compact bone. And in order to create our compact bone, we have to have multiple units of this functioning osteon. You might be wondering, okay, well, what is the osteon? What are the components that make up the osteon in the first place? Well, first of all, we need cells, right? Obviously, everywhere in the body, we're going to need cells. So the cell type of use that's going to be found in bone is going to be the osteocyte. So if we break up that word, cyte refers to cell, osteo refers to bone. So our osteocytes are going to be the main functional cells that are going to be found in the bone. Now, living inside a bone is fairly hard. It's kind of like living inside of a concrete house almost. These osteocytes would suffocate if the bone just existed completely, the opposite of hollow, completely filled in. That's why our osteocytes actually require lacunae to step inside of. So all these dark spots right here are lacunae, which are pretty much little hidey holes where our osteocytes reside in. So our osteocytes are going to reside within lacunae to make sure that they're protected and they have enough room to kind of like live essentially instead of living inside of this concrete jungle gym over here. Now, obviously, in order to function properly, our cells still need to be able to communicate. And one of the main ways that these cells are going to communicate is through the caniculi. Now, the caniculi are these small little canals that are going to connect the lacunae between each other, as well as connect the central canal with all the lacunae. So the caniculi are essentially gap junctions, and we've already talked about gap junctions between cells before, where they allow for different chemical messengers and ions to bypass through to each cell. So these caniculi are going to serve as gap junctions, essentially. And then finally, the final component we have are central canals. So these central canals are found in the center of the osteon, and this allows for vertical traveling of our blood vessels. So we have arteries and we have veins that are going to be traveling inside the osteon. Now, we also have an additional type of canal besides our central canal known as perforating canals. So here you can see perforating canals and central canals kind of side by side. Now our central canals are known for just going vertically up and into the osteon itself. The perforating canals are the perpendicular canals that are going pretty much left and right and traveling through the bone. Now both the central canal and perforating canal both have alternative names that we have to know. So the central canal can also be known as the Haversian canal. That's kind of where we get the name the Haversian system. And then the perforating canal is also known as the Volksmann canal. So do make sure that you guys are aware of both of those names, the Volksmann canal and Haversian canal. And I'll point them out whenever we see it in the slide too. I went back here real quick because I just wanted to talk about the periosteum real quick. The periosteum is one of the outer layers of the bone. So if we look at the word peri refers to around. So it's going to be around the bone. And periosteum is important because this is actually where our nerves are going to be traveling along the bone. And our nerves are actually what indicate, a fractured bone, for example. So that would be a result of the periosteum. The periosteum is also really good for attachment of our tendons and ligaments. So at the site of the periosteum is where our tendons and ligaments will be attached onto. Let's see, we pretty much covered just about everything we need to here. All right. So, taking a look at our cartilage. Now, first thing we need to know is that our cartilage are all made up of chondrocytes. Right? So, our chondrocytes, if we break up that word, site refers to cell, chondro refers to cartilage in this case. So our chondrocyte is going to mean a cartilage cell. Now, this is a simple pattern that I picked up on back when I was first studying it, and I think it's a pretty useful pattern when used to identify the cartilage. Now we have three different types of cartilage. We're going to have elastic, we're going to have hyaline, and we're going to have fibro. There we go. So we have three different types of cartilage here: elastic, hyaline, and fibro. And what I started to notice was as we kind of went up this list from fibro to elastic, we actually increased in the number of chondrocytes. So we're actually increasing our number of chondrocytes. And what I saw with this increase of chondrocytes, is we saw an increase in elasticity as well. So as we have more chondrocytes, we have like an idea of more elasticity. And I kind of want to show that to you guys as we kind of go through the PowerPoint. So taking a look here, I'm going to start with elastic cartilage first. This is the top of our list. This is the one with the largest number of chondrocytes. As you can see here, there's just a plethora of chondrocytes. Now, the elastic cartilage is going to be the most flexible because it has the most cartilage, right? So this is extremely flexible. This provides a lot of support and is able to tolerate lots of distortion without any kind of repercussions. And one of the biggest areas that you can find this is on your ear. So your ear can deal with this elastic cartilage, as well as the tip of your nose, and a few other areas that really require that lots of stretching to kind of be able to maintain their functioning. Now here we see our hyaline cartilage. So our hyaline cartilage doesn't have nearly as many chondrocytes. Wherever I put this, there we go. Our hyaline cartilage doesn't have nearly as many chondrocytes as our elastic connective tissue, so that means that it's not going to be nearly as elastic, but that's also a good thing because as we decrease the elasticity, we're actually going to increase our structure. and basically how tight our structures are. And this is actually what we want for our hyaline cartilage. So in our hyaline cartilage, one of the biggest areas that we can think of where hyaline cartilage is found is inside of our joints. Now for our joints, you want them to be fairly flexible, right? You want to be able to move still. However, you don't want to be so freely movable that your arm is just dislocating out of it and popping out of its socket all the time, or being able to stretch. We want some more of that structural integrity for our joints, and that's why hyaline cartilage is the perfect idea of what we should use there. Now, one other thing too, for kind of like identifying these structures for hyaline cartilage, is that hyaline cartilage has a very glassy look, like as if you were looking into a lake that's very clear. It's almost like a mirror. I also like to think of like a painted church windows. That also really reminds me of kind of like hyaline cartilage look, and we'll kind of see that in the next few examples too. But before that, let's get to fibrocartilage, the final type. So the fibrocartilage, this has the fewest number of chondrocytes, which means it's going to be the least elastic, but that makes it extremely durable and really tough, and it can resist a lot of compression and shock. One of the biggest and most important areas that we'll find this in is in the intervertebral disc. So that is going to represent the disc that sits in between the vertebral column, and it's going to prevent bone to bone contact. It does limit a lot of movement because once again it's not very elastic, but it does give us a lot of strength when it comes to our vertebrae. And that's kind of the strength that we need. This literally gives us our backbone. So you can also think of areas under intense compression would be the pads within your knee joint, pubic bones, and intervertebral discs, etc. All right, so that concludes the connective tissue slides. Now, what I want to do real quick is just kind of take a quick look over the histology review of the various aspects that we have. Let's see, Control L, perfect. All right, so first up for our epithelial tissue. Here we can actually see a simple cuboidal epithelium. So if we're looking at this is our lumen right here. This difference in color would be the basement membrane. We can count the nuclei from the lumen to the basement membrane. It's just one nuclei. And this is a very square or very cube shaped. Now you might be wondering, okay, well then what's this? Or what's this? Or what's this? These are all their own individual and independent lumens, and then the surrounding area is their own independent basement membrane. So the way that our simple cuboidal works, remember that the function is secretion and absorption. They often come in tubules where they're making their own tubes that are all going to eventually go to the same location. But for now, we have all of these individual locations that we're looking at. So remember, we're identifying the lumen and then the basement membrane. Taking a look here, lumen, basement membrane is where we're getting much darker color. And then we're going to count the nuclei going all the way up. That's obviously going to be more than one. And we have a very squished look with multiple cells on top of one another. So this is going to be our stratified squamous epithelium. And remember, we got to specialize, is it keratinized or non-keratinized? As we look at the lumen, there's just open space. The most superficial layer of our cells all have nuclei. So this would all be considered non-keratinized. Here, taking a look at this slide, this one's a little bit harder to see, so let's see if we can actually break it up a little bit. Now, we can obviously identify this as the lumen, but as we see, our cells are not exactly in a straight line. They actually dip down and come back up. This is actually a very useful idea in the digestive tract to increase surface area. But besides that, here we can actually see the darker color. This would be around where the basement membrane is occurring. And here would be the lumen, and still, even in between these gaps, this would all still be considered the lumen, because this is just increasing the surface area. And we can count one nuclei here from the lumen to the basement membrane. That one nuclei is representing our simple columnar epithelium. Sorry about that. Taking a look here, we have, once again, a simple columnar ciliated epithelium. So ciliated is referring to the fact that these guys have cilia on top. And once again, basement membrane, lumen, only one nuclei, and they're very column shaped. Taking a look here. So we can identify the lumen all the way up here, But it also looks like there's some gaps kind of occurring down here as well. And you might be wondering, okay, well, why is that the case? Well, first thing we're going to do is we're going to identify the basement membrane. So where it starts to turn from this white to this pink area right over here, this is all going to be our basement membrane. And what we see from the basement membrane to the lumen is multiple cells right here. These are all nuclei, so this would be stratified, right? And then these cells all look very squished, so this would be our stratified squamous type. But looking over here, we don't have any nuclei found in this entire mass right here, which means all these cells are dead. So that's going to help us narrow down the choice to stratified squamous, keratinized epithelium. So it's going to be our stratified squamous, keratinized epithelium because the keratinocytes produce enough keratin to kind of kill off these cells. This is a good example of what we can see inside of our skin as the most superficial layer. Let's go ahead and actually magnify here. So this is actually where we can see more of the nuclei here. The basement membrane, lumen would be up in this direction where the keratin is. Oh, and there's our answer. Look at that. Taking a look here, there's actually two different types of epithelium found here, and this is all found inside the kidney. So first of all, we see a lot of lumens right along here, and all of these lumens are kind of representing, basically little tubules that can be secreted into. Right, we've seen this once before, and that's with the simple cuboidal epithelium. So that's the most common shape that the simple cuboidal epithelium will take place in. But if we look over here, we have a very thin line found in between these guys that's allowing for simple passing over of diffusion of various molecules. And this is actually very useful to keep simple squamous epithelium here. So I know it's a little bit hard to see. You guys don't have your histology adapted eyes yet, but our simple squamous epithelium can actually be found at this exact layer because this is allowing for an easy diffusion of various molecules that are going into be micturating. Once again, this is all going to be simple squamous epithelium around here, this thin line, while this is all simple cuboidal. Taking a look at these very tiny cells, this is actually found inside of the alveoli of the lung. We already know what kind of cells we need inside of the alveoli inside of the lung. That's going to be our simple squamous epithelium. Taking a look here, we have some more different tissues. Lumen, basement membrane, multiple cells, no dead cells. This is going to be our stratified squamous epithelium. We've already gone over this one. This is going to be our stratified squamous keratinized epithelium. Sorry, I also forgot to mention this one's non-keratinized. It's a good idea to mention that. Alright, taking a look at this guy. Once again, we have this natural format of multiple lumen and multiple tubules, right? And there's only one kind of epithelium that we've seen that does this over and over again. And this is going to be our simple cuboidal epithelium. Taking a look here, this one does get a little tricky. We have seen these circular tubule formations before. These circular tubule formations are all useful for identifying our cuboidal type, but in this case, we actually have multiple nuclei between the lumen and the basement membrane. So this would actually be one rare example of the stratified cuboidal epithelium. Taking a look here, we've already been inside of this colon before. We already know this is simple columnar epithelium. Yep. Alright, taking a look at this guy. We have our lumen, we have our basement membrane, and we have kind of a column shape going on, but more than that, we actually have multiple cells stacked on top of each other. So in this case, we're going to be dealing with stratified columnar epithelium. Taking a look over here, we have our pseudo-stratified ciliated columnar epithelium. Now the reason why I'm kind of going with pseudo-stratified ciliated is because out of the examples, our stratified columnar does not have any cilia. But in this case, this guy very evidently does have cilia, and this is going to be found inside of our respiratory tract with the multiple nuclei stacked on top of each other. This is just going over examples of what happens when smoking. Taking a look here, we have our transitional epithelium. So this is all our transitional epithelium. This is allowing for expansion of the urinary bladder. Whenever you're seeing urinary bladder, you're only thinking of one type of epithelium, and that's going to be transitional epithelium. Alright, so connective tissue. Alright, we got multiple wavy lines of collagen. They're all in a very straight pattern. this is going to be our dense, regular connective tissue. This looks like our Van Gogh Starry Starry Night. This is going in multiple directions. So this is going to be our dense, irregular connective tissue. Down here, once again, we see multiple layers all kind of branching out into their own area. So this is going to be the dense, irregular connective tissue. Here, once again, we know that this is in the region of the skin. We know that this is our keratin, or our keratinized cells. This is our stratified squamous keratinized. But looking underneath the basement membrane, right? Remember that looking underneath the basement membrane, we're going to find our connective tissue. And this connective tissue in this particular instance is going to be our irregular, or dense irregular connective tissue. So you can see how it's all kind of going together now. Okay. Kind of keep moving. Identified in the ligamentum flavum. This is going to be our elastic connective tissue. So this is going to be the dense elastic connective tissue because once again we have multiple collagenous fibers working together, but we still have some spacing that allows and permits expansion to occur and contraction. Once again, this is going to be our elastic connective tissue. This one's found in the aorta. And now we can see a lot of these collagenous fibers working together with some spacing that occurs in between. Looking at this tissue here, we see a lot of open air that kind of exists between all of our fibers. So this would be our loose areolar connective tissue. Here it's just going over the skin again, so papillary and reticular layer. So dense irregular up here, loose areolar, it's going to be in the P area. Taking a look here, we have these nice round circles. So these nice round circles are our fat droplets, or our adipocytes. So this entire tissue made up is going to be the adipose tissue. That's the one that insulates heat. That's the one that actually gives us a lot of energy. Once again, we have our adipocytes, our adipose tissue. Some students get a little confused and may call it dense irregular connective tissue because it looks very erroneous over here. But if we actually notice, we have almost seemingly perfectly formed circles, and that always represents our fat cells. So this is all going to be adipose tissue. Taking a look here, this is going to be our reticular tissue. You can kind of see, almost like it has like a old Western film image over it. That's what I always think of whenever I see this reticular tissue. Once again, this kind of film that we see over it, this is going to indicate reticular tissue. This is just blood. Remember, our erythrocytes, platelets, and lymphocyte. This is just going to be blood. Once again, more blood. Taking a look at this type of tissue type, we have our bones. So more in specific, we have our cortical bone, or our compact bone. This is the outer layer of the bone that we see. And actually getting in a zoomed in look, we can actually identify the central canal, the lacunae with our osteocytes, and the individual caniculi that are going to connect all of them. And then we can refer to this entire thing as an osteon. So you can kind of see that there's a lot of different questions that we can generate from this alone, from this image alone. Now this look is something we haven't really seen before. This is actually going to be our trabecular or spongy bone. So do you guys see all of this kind of occurring right here? This is all of the branching that we've seen before. So this is all that branching that occurs to disperse the force of the bone. Taking a look here, we're actually going to zoom in on this little green box right here. This is inside the trachea. This is our hyaline cartilage. So our hyaline cartilage is what gives that really glassy look, and there's a mild amount of chondrocytes. All of these cells are our chondrocytes. Looking at this once again, very glassy look. So even though there's an incredibly amount more of chondrocytes, this is still going to be our hyaline cartilage. So this is still going to be our hyaline cartilage. Looking here, we no longer have that glassy look, and we have multiple chondrocytes found throughout. And it also gives us the indicator that it's found in the epiglottis and the earlobe. This is going to be our elastic cartilage. Once again, multiple chondrocytes. This is going to be our elastic cartilage. Here, this is found in the vertebral disc. We see few and far in between chondrocytes. This is going to be our fibrocartilage. And then once more, this is once again another example of our fibrocartilage. All right, and that concludes this video.